Hi everyone! The purpose of this video is to walk through pKa, pKb, Ka, and Kb. Give you an overview of what those terms mean, why we use them, and how to manipulate them. Alright, so pKa, pKb, Ka, and Kb, these are all ideas we use for weak acids and weak bases. They're not dissimilar from pH and the concentration of H+, which we can use in any situation, but in order to find the concentration of H+ for weak acids and bases, we know weak acids and bases don't fully dissociate, so it's going to be a little bit more complicated to find the concentration of H+ if you only had the pH. And that's where pKa, pKb, pKb, and Ka come in. So with pH, we already know that pH is equal to negative log base 10 of H+, and H+ is equal to 1 times 10 to the negative pH. Well, pKa and pKb are really function really similarly. So the pKa is equal to negative log base 10 of Ka. Same way pH was equal to the concentration of H+. pKb equals negative log 10 Kb. And then Ka and Kb, these are not just the concentration of H+, like we saw before. Ka and Kb actually describe equilibrium constants for the dissociation of weak acids and bases. Weak acids and bases. So for strong acids and bases, it's pretty simple to know the concentration of H+ because it's going to be the same as the concentration of the acid. Or, well, OH for a base. So the same as the concentration of the acid for strong acids. But for weak acids and weak bases, we need to consider that not every single molecule dissociates. And so we actually need to look at the equilibrium constant to determine how many of my molecules are dissociating. So instead of just looking at H+, I'm going to look at the equilibrium constant for the dissociation of my acid or base. All right, let's see where Ka and Kb come from. So, of course, equilibrium, the dissociation of an acid, we've written out this equation many times at this point. For a weak acid, we have your acid plus water yields conjugate acids and conjugate bases would be your acid without the proton plus H3O plus. Weak base would look similar, but we'll do bases in a moment. And then we just wrote the equilibrium constant expression, just like we did in topic 7. Water is essentially a constant. You could multiply both sides by H2O, or the concentration of H2O. And so Kc times the concentration of water, which is a constant, is equal to Ka. So Ka is the concentration of H3O plus times however much of your acid dissociated over the concentration of your acid that did not dissociate once it's been added and reached equilibrium. So, of course, for pH, I only need this concentration of H+, but for a weak acid, I need to consider that not all of my molecules have dissociated. So that's how I got Ka, Kb, same exact thing. Oh, so sorry, here's an example. So this would be for the dissociation of CH3, COOH. So I'm just writing the constant expression, very similar to Kc, just not looking at the water reactant. Kb, very, very similar. So our reaction, we're looking at conjugate base, conjugate acid. In this case, water is acting as an acid, and its conjugate base is here. We've written out the expression. All right, so again, you can write the Kb expression. This would be for NH3 acting as a base. So when NH3 acts as a base in water, it doesn't really dissociate. Remember, strong bases, we're not so much thinking about dissociation. we're trying to find if this is my conjugate base, we're identifying what the conjugate acid would be. And the conjugate acid, of course, would be 1 proton more and plus OH minus, which is a conjugate base. Water, we don't need to consider because it's a constant, so I'm just taking the concentration of NH4, concentration of OH minus, over the concentration of NH3. All right, so that's how we find Ka and Kb. If we just need to find Ka and Kb, we can also relate them to these things called pKa and pKb. These give me an indication of how strong or weak an acid is or a base, but they only work for weak acids and bases. So relative strength of weak acids and bases. So within all of the weak acids and bases, is one weaker, is one stronger? Instead of using pH to figure that out, I'm going to use pKa and pKb. You can also calculate the pH for weak acids and bases. We haven't done that piece yet. There will be a way that we link pKa and pKb to pH, and that's what we'll do the next time we gather in an HL session. So like we already talked about, pKa is negative log base 10 of Ka. Kb, same thing, but with Kb. Ka is 10 times the negative pKa, so this is just relating these two expressions. And again, this time, unlike with pH, where you'd just be looking at H+, we're looking at the equilibrium, the dissociation of my weak acid, because we know not all of those acid molecules dissociated. So this is giving us a sense of the concentration of H+ compared to the concentration of molecules that did not dissociate. So we end up with these really important relationships. Ka times Kb equals Kw, which we learned is 1 times 10 to the negative 14 at 298 K, but it is temperature dependent, so it varies by temperature. pKa and pKb equals pKw, and pKw is 14 at 298 K. All right, so let's practice that. Before we practice, so again, this is used to compare relative strength for weak acids and bases only. So when I say stronger, I mean out of only weak acids, and same with bases. So a lower pKa is a stronger acid, just like a lower pH is a stronger acid. One thing to note here with bases is that unlike with pH, a lower pKb actually indicates a stronger base. It's more like POH. So a high Kb, this indicates high dissociation, or at least becoming conjugate acid like you would with ammonia, which leads to lower Kb, and a lower Kb is relatively a stronger base. We're still just talking about only weak bases. All right, so for now, all you're responsible for is converting Ka to pKa, Kb to pKb, and relating the two. So, for example, for HF, pKa equals negative log base 10 of Ka, which is 5.62 times 10 to the negative fourth. I'm just going to plug that into my calculator. Negative log base 10 of 5.62 times 10 to the fourth, or e to the negative 4. And my pKa that I get is 3.25. And so this would be 3.25. All right, finally, the last piece here is dealing with the conjugate base. And so the conjugate base of HF is F minus, just the difference in one proton. And now if I have Ka and pKa, I should be able to find Kb and pKb. So you could either focus on the pKa's or on the Ka's. Let's just do the Ka's, Kb's, because it comes first. So Ka times Kb is going to be equal to Kw, just like we saw right here. And then Kw is 1 times 10 to the power of negative 14 at 298 K, which is what we have. So I have 5.62 times 10 to the negative 4 is Ka, times Kb equals 1 times 10 to the negative 14. Now be kind of careful when you put this into your calculator. It's an easy mistake to make. We're going to put in 1e negative 14. E indicates times 10 to the power of, so it's 1e negative 14 divided by 5.62e negative 4. That looks good. Kb equals 1.78 times 10 to the power of negative 11. 1.78 times 10 to the power of negative 11. And now pKb, well, pKb is equal to negative log of Kb, or 1.7 log base 10, obviously, 1.78 times 10 to the negative 11. So I'm just going to leave that in my calculator, do negative log of second answer, and my pKb is 10.75. 10.75. I can double check myself that that's right, because pKa and pKb should add up to 14. 10.75 plus 3.25 does indeed give me 14. You could have started with the 3.25, finding pKb with this 14, and then also worked backwards to find Kb. Hope that helps. Let me know what questions you have. Thanks.